All right, welcome to Chapter 2, Acids and Base lecture. So, what hybridization is the underlying carbon in the following molecule? This is review from Chapter 1. So hopefully you can draw your Lewis structures or stick structures, line skeleton structures is what I do. So that's CH3, CH3. And then this is that red carbon, and then this is CH and CH. That's going to be a double bond, CH, CH. And then we'll do this one, CH2. And then this is an aldehyde, CHO. So this is that molecule. And then the question is, since this carbon has 1, 2, 3 things, the H is there, so 3 bonds, because carbon has to have 4 bonds. So this has 4 groups bonded to the carbon. So sp3, you add your superscripts, and you see that they total to 4. So sp3, what do we know about sp3? It's tetrahedral. This is the hybridization, which tells us it's tetrahedral with 109.5 degree bond angles. All right, so the answer is C. All right. Now, when we're talking about acids and bases, there's different types of acids and bases. This is Bronsted-Lowry acids and bases, and it has to do with a hydrogen atom. And this is where we're going to assign pKa values. pKa, you can review pKa. pKa from Chemistry 112 is the negative log of the Ka value. Ka is your equilibrium of products over reactants, and it's specifically for H3O plus, and it gives you a concentration. What you need to know is the lower your pKa value, the stronger the acid. Okay, so the lower the pKa value, the stronger the acid. So if you have a low pKa value, that means that molecule wants to give away an H plus. So like HCl, it's not going to be HCl. It's going to be H plus and Cl minus. Okay, because an acid wants to give up a proton. And the base is a proton acceptor. So you don't actually have to know these definitions, but you need to be able to apply these pKa values. And you have 2 Pogel activities. You have Pogel 3a and 3b, works through models for these concepts. You also have a pKa table that I would recommend you print that off and use that. Most of my students always have to memorize that in a face-to-face class, but you'll want to utilize that pK value for all your assignments in here. Okay, so a conjugate base, so this should be CH3OH. This is methanol. And a conjugate base is, so an acid, so if this was an acid, its conjugate base gives up a proton. So CH3O minus would be its conjugate base. And so that would be C. Now, so types of Bronsted-Lowry acids and bases. The acids are here. These in red are the protons that are given up. And so a conjugate base of, let's say, acetic acid would be this. Okay, and then it gives up its proton. The conjugate base of H3O plus would be water. Now, Bronsted bases will accept a proton. So water is a base, so its conjugate acid would be H3O plus. Ammonia, NH3, that's in Mr. Clean. When its conjugate, so if this is a base, it has a conjugate acid, and that would be NH4 plus. So acids and bases are very important in molecules. This is morphine, and you're looking for the hydrogen atoms, and they can either act as acids or bases depending on a particular reaction. So I can tell you this right here, that would act as a base, this functional group here, this amine. And you can tell because it has a lone pair. And a lone pair is going to want to accept a proton. Okay, so that would be that. Where your acids, those are your acids. And when you look at a pK value, and you need to start looking at these pKa tables and learn how to read them. Can you see, if you've printed off that pKa table, can you see what the pKa value of this one is? And what's the pKa value of this proton? What's this conjugate acid? It would be, once you remove the hydrogen there, this is a phenol because of the aromatic ring, and that is a pKa of about 10. This is an allylic alcohol, and I'm going to say it has a pKa of somewhere around 16. Okay, so this would be your more acidic proton because 10 is less than 16. Now keep in mind there's hydrogens everywhere, right? There's hydrogens on here, there's hydrogens on here, there's hydrogens here. These aren't acidic protons. And we're going to talk about the factors that determine what makes a proton acidic. So you need to be able to, so one of your I can statements, I can draw acid-base reactions. And in doing so, you need to be able to predict the equilibrium. So these are the way you predict the equilibrium values based on the pKa's. So you're going to have to assign pK values. To be able to draw acid-base reactions, you got to be able to assign pK values. You're going to have to be able to pick out the equilibrium values, and you're going to have to write conjugate bases and conjugate acids. So you're going to be given an acid and a base. You have to decide where's the acid, where's the base. You have to draw the curved arrows. These are the curved arrows. And then you have to draw the conjugate base and conjugate acid and be able to assign pK values. Now, let's look at pKa. pKa, the A means acid. So you would only assign a pKa value for the acid. So there's an acid. So you have an acid and base on the reactant side. And then on the product side, you always have your conjugate base and conjugate acid. So you would only assign a pKa to the conjugate acid. You see the A? You do not assign pKa values to bases, okay? So this gives us two numbers. This is a number, and this is a number. And we can compare those. And that'll determine which way the equilibrium goes. So this is an example. Okay, so this is a base. It has lone pairs and a negative charge, okay? So it's going to take its lone pairs, and it's going to go and take that hydrogen, okay? And so this is a new bond. Whenever you draw this, this is a new bond. So these electrons here has become now that bond. And since this is the proton, this is your conjugate acid. And this water donated its protons, so there's the electrons that go onto the oxygen. And so there they are. And there's your formal charge. So this is your conjugate base. Acid, conjugate base. Base, conjugate acid. Now we assign pKa values. So you get your pKa table, and you'll see that water has a pKa of 15.7, and you'll see that ammonia has a pKa of about 36. Sometimes you'll see it 35 or 36. Okay, so this is not right, and I don't expect you to do equilibrium values like that or you'll get it wrong. I expect you to show the equilibrium goes to the your equilibrium. You might want to write this down, lies toward the higher pK value, aka weaker acid. So which way would I do this? 36 is higher than 16, so your equilibrium value would go there. And so this might be 95%. This could be 5%. And so when you put this in a flask, if you put water and this NH2 in a flask, you could say probably 95% is going to be in these forms. Now, what's the difference between this pKa value? If this pKa, let's just say this is 16, and this pKa is 36, what's 36 minus 16? 20. So are we talking about 20? We are not talking about 20. We are talking about this number here. I got to do 20 zeros. 3, 6, 9, 12, 15, 17, 18, 19, 20. Oh no. Don't know what happened there. Kind of cool, but not what I wanted. So we're talking about 20 zeros. 3, 6, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if you don't think that's a big number, that's a very big number, put a dollar sign in front of that, right? Someone owes you $20 versus someone owes you that many dollars. See, that's how, this might actually be more like 99.5% over on this side of the equation. That's the power of these pKa values. Okay, so here we have an acid and a base, and I expect you to be able to write these reactions and predict them. And that's why you want to work through your POGL. Okay, so HCl, that's an acid, and you put it with methanol, and that's a base because it has these lone pairs, and these lone pairs are going to, you got to be able to draw these curved arrows, they're going to go and get a proton. And when they do this, see, this is where they're going. This arrow here actually represents these electrons. Okay, so the arrow means these electrons. You'll see in chemistry we do fishhook arrows sometimes. That's when you have a single electron. But we don't do that right now. So here we have 2 electrons. These are them, and they're going to go grab this H. And so this is the acid goes to the conjugate acid, or the acid goes to the base here because it loses the proton. But this base goes to the conjugate acid here and gains this proton. So that's these electrons. And so this is the conjugate acid. And what's the pKa? You need to be able to read that table. I think you'd find it's about 1.7, something close to that. The acid here, HCl, is like a -10 because these are inorganic acids. So which way does the equilibrium lie? It lies to the higher pKa value. So you draw your equilibrium values like that. And this is higher. And let's just round this to 2, and this is -10. What's the difference there? 12 zeros. Okay, so we're looking at, that's how many times this is going to lie to the product. So they're talking about the equilibrium arrows, and here we have the same thing here. This looks the same. All right, write the acid-base reaction of methanol with sodium hydroxide. This is what you want to be able to do. You want to be able to say CH3OH plus sodium hydroxide, and I want you to label this. This is an acid, and this is a base. Let me tell you how you know that. Whenever you see any of these metals, that's a plus, that's a negative. Okay, and so go ahead and draw your Lewis structures, and that shows you that that's your base. Anytime you have a negative charge, that's going to be a strong base. You can't get more negative than a negative charge. And lone pairs, that's a requirement for a base. Now, here we have the acid. And for what you're doing right now, I want you to draw out your entire Lewis structure because you're just learning. So that's what I expect. All right, so this is an acid. We have to label them, and this is the base. And so now we're going to draw our curved arrows. So these lone pairs here, we're going to go and take the proton, and then these electrons are going to go back on the oxygen. And so then you want to draw on the product side the conjugate base. We'll just do CB, conjugate base. And then the conjugate acid is water there. Okay, and so the acid gets a pK value. You can look at your table. Methanol, you're looking at about 16, and the pKa of water is about 15.7. So at this point, if you're just 10 or 100 times different, those are going to be these equilibrium values where they're 50% products and 50% reactants. What is the acid in this reaction? So here the acid is methanol. General reactivity. Okay, so like I said, bases are electron rich, especially if they have a negative charge. Acids are electron deficient. So a lot of times the acid proton could have a partial positive charge or a positive charge. So like H3O plus, that's an acid. And if you drew the Lewis structure of that, you would see it wants to give up the proton. Bases, ammonia is one of your bases. Another base you might see is like lithium methanol or lithium methane. Well, you should know that because lithium is positive. You'd have to draw your Lewis structures. That would give a lone pair on the carbon. Okay, this would be a very, 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 very strong base. So acids and bases react with one another. This is your first reaction. By the time you get done with organic 2, you'll have probably about 180 reactions. And this is your first reaction. So acid strength and pKa. So I've told you the lower your pKa value, the stronger your acid. So you want to be able to assign pK values to acids and conjugate acids. We do not assign them to base. The more readily a compound would donate a proton, the stronger the acid is. It's a measurement of strength. Just like if I say 6 feet tall versus 4 feet tall, that is a measurement of height. You know that 6 feet tall is taller person than a 4 foot tall person. Okay, so this is pK is a measurement of acid strength. The A means acid. The lower the pK value, the stronger the acid. All right. And they're just showing you this. I'm not worried about the Ka, but this is good. And they're showing you the Ka there as products over reactants. It's a measurement of how much H3O plus is generated. And the pKa, the little p always means negative log of whatever. So like pH is negative log of your H3O plus concentration. It's just a mathematical term. They're showing you that the different Ka values when they're converted to pKa. So this is what's important right here. The smaller the pKa value, the stronger the acid. S and S. Smaller, stronger. Smaller, stronger. And so you have a pKa table that I have given you with functional groups, and that is in Chapter 2 in your course documents. I would print that off if you could. You're going to need that, and that will help you. And I will let you use that for your quizzes and your assignments and your exams. Okay, so, but you're going to have to do some Pogles and do some stuff, and you're going to have to learn how to read that pKa table to use it effectively. But it is your friend. Okay, so looking at the different strengths. So here's your acids. You see the protons are in red. This is acetic acid, and it's about a pKa of about 5. I usually do numbers of 5 because I actually have them memorized in my mind. I said this was a -10, so you can see if you get around the ballpark, it's 15.7. I just go with 15.7, but it is closer to 15. Your alcohols, these are alcohols. When you start learning functional groups, okay, FG means functional groups, you'll start looking at, okay, this is an alcohol. An alcohol is an oxygen bonded to a hydrogen. Those are 16, unless they're a phenol. This is an aromatic alcohol. And I would just recommend you go ahead and start learning those functional groups. That is a pKa of 10, and you will need to know that. This is hydrogen gas, pKa of 35. These tend to be basics. Okay, these are not strong acids. They're not strong acids, okay? This is ammonia, 38. A lot of times you'll see me say that's 35. I just kind of go with 35 here. You'll see me say, okay, this is an hybridized sp2 carbon hydrogen. That's what that is, sp2 carbon hydrogen. And I'll say that's probably 45. This is an sp3 carbon hydrogen. We'll talk about hybridization and pKa values. That's a 50. All right, so this is exactly what I need you to be able to do. This is an alkyne. An alkyne is an sp carbon hydrogen. That has a pKa of 25. Okay, and so this is your base. Now what happens here is you need to be able to write your curved arrows. That's your mechanism, folks. And so this, and you label this base is going to take that proton, and then those electrons are going to go onto that carbon. So you can see those electrons when they go onto that carbon, and you have to be able to draw the products. That's what it means to predict it. You need to be able to draw this conjugate base, and then the base here, when it takes these electrons and takes that hydrogen, it now makes this NH2 goes to NH3. So it used one of those lone pairs. That's ammonia, and that's your conjugate acid. And the pKa of that, and I would probably just say 35, but you're in that ballpark. I'm happy with that. And you have the paper, to whatever your paper says. Okay, but now you want to compare. You want to compare 25 with 35. Well, 35 is bigger, and it's bigger by what, 10 zeros? Yeah, okay, so it's 10 zeros, and so there you go. You want to point towards the higher pK value, which is your weaker acid, and that's the direction of your equilibrium. Write the acid-base reaction of methanol with sodium hydroxide. So we're doing this one again. Whenever you see sodium, lithium, magnesium, any of those metals, just go ahead and make that a plus and that a minus. And I would like for you to draw out your Lewis structures on these while you're learning Lewis structures. So these are your Lewis structures, and what's happening here is this is going to go take that proton, and then those electrons are going to go onto that oxygen. And so this is your acid, because this is the proton that's being taken, and that would make this your base. And you're going to notice your base anytime you can find your negative charge or a lone pair that's reactive. Now we've got to predict our products. So now we're going to do the result of this. Well, methanol lost the hydrogen. So there's that lone pair there, and that makes it a formal charge is negative. And then you have the OH here, and well, there's the lone pairs there, and there's the hydrogen. So this is your conjugate acid, because that's where it went. This would be your conjugate base. We don't really care about the conjugate base. Where did the sodium go? Well, the sodium's going to hang out where the negative is. So you can just, if you want to put that in there for conservation. Now we want to assign pK values. Well, you look at your chart. This is pK of 16. Water's about a pK of 15.7. So your equilibrium values are going to be like that. Now what is the pK of the conjugate acid? So 15.7. In this case, I would accept 15 or 16. Write another reaction, acid-base reaction of NH2. So NH2 and negative lone pair with CH. So this is an alkyne. And so this is your base. This is your acid. What's your pKa? That's an sp3 carbon hydrogen. pKa is 25. And now we're going to draw the reaction. You always draw it from the base to the proton. And then those electrons are going to go onto the carbon. And so then we want to draw our products. And then there's your conjugate acid. And then your conjugate base would be this here. And that would be a formal charge of negative. Now we assign our pK values. pK, we said this one is 25. pK value of this, you look at your sheet, hopefully you came up with 35. 25 and 35, it's going, that's 10 zeros. And towards the higher pK value, so it's going to be toward the product. Okay, so that was the exact reaction we just did. You see the curved arrows, everything's labeled, and this, your book is not right on this, it should be like that. And this tells you what to do. And we just did that one, towards the product. Factors that determine acid strength. Okay, now you do have a POGL on this, and this is important. These are the 4 factors. And sometimes I'll be like, okay, why is this pK lower than this other pK? So it's just like this. So this has a pK of 10. This has a pKa of 16. Now why? It's one of these factors. The answers are, the why is always one of these factors. Well, this, the way you do, when you're trying to explain why, you always draw the conjugate base and you compare the stability of the conjugate base. So what's the conjugate base of this one? Well, the conjugate base would be this. What's the conjugate base of this one? Now, can we draw any resonance structures on this? No, because this carbon is sp3 carbon. So there's no resonance structures. So you could just say there's just one, and that's itself. Now this one has an sp2 carbon, so this can go here and this goes here. Okay. Then we can draw another one. So in this, I'm explaining why. You will have to explain why. So pay attention. In fact, I forgot that one there. That goes there, that goes there. So this is another reason why you need to practice drawing your resonance structures. The best thing to do that is to spend some time with your POGIL exercises. There's 4 resonance structures for this one, for the conjugate base. There's only 1 resonance structure for this conjugate base. Which one's more stable? Resonance always wins. Okay, so resonance effects is why. This conjugate base has 4 resonance structures. This conjugate base has 1. This conjugate base is going to be more stable, so it's going to be more stable when the hydrogen leaves. It's all about how stable is that conjugate base when the hydrogen's taken away. Now, you want a number of how much it is? What's 10 minus 16? It is 1,000,000 times more stable. That conjugate base is 1,000,000 times more stable because of the resonance effects. Okay, so we're going to look at each 4 of these. So you always draw the conjugate base, and then you determine which conjugate base is more stable. And the more stable the conjugate base, the more acidic the acid. And then you have to apply one of these 4 factors. So why does water have a lower pKa value than methane? So we draw the conjugate base. There's the conjugate base, OH. And then methane, when you lose that conjugate base. So we're comparing these conjugate bases. Well, they're not resonance. There's no resonance structures. Remember, there's 4 factors. This one is the electronegative atom. Electronegative atom. So you might remember in your major resonance structures, the negative charge is more stabilized on the more electronegative atom. So oxygen is more electronegative than carbon. So this one's going to be more stable. And so then this one's going to be more acidic. So water has a pKa value of 15.7, and methane has a pKa value of 50. It costs 50 to remove that. It only costs 15.7. So it's because the oxygen is more electronegative than the carbon, so it can stabilize the negative charge from the conjugate base more easily. And this is called an element effect. Okay, this is an element. The element is more electronegative. Here we can see this going across the second row, second period. pKa of 50. The nitrogen, pKa, I say about 35. Oxygen, 16. And then HF is, so HF is about 3. So these are the conjugate bases we're looking at here. Okay. Rank the following compounds from most acidic to least acidic. Okay, so here if you drew out your Lewis structures, and I'm sorry that these superscripts get lost when I make this a PDF file. Okay, and then we have this one. So always draw your Lewis structures to solve your problems. Now we got to find the acidic proton. So we're talking about this one, we're talking about this one, we're talking about this one. So then if you drew your conjugate base to explain why, there's that one. These are your conjugate bases. This is how you solve the problem. We don't use a calculator, but we do need to draw Lewis structures and apply the concepts in this organic chemistry. Okay, so you see that we're not comparing the conjugate bases. We're not looking at resonance because each one of these carbons here next door is an sp3 carbon, so it cannot participate in resonance, so they're all having one resonance structures itself, its structure. But we're dealing with this negative charge is on the carbon, this negative charge is on the oxygen, this negative charge is on the nitrogen. So this one's going to stabilize the negative charge the most. So the most acidic would be number 1, because it's going to be the most stable. And then this would be number 2, and then this would be number 3. So number 1 is the alcohol here, and number 3, so this would be your answer. Okay, now other element effects we need to think about is the size, not just electronegativity. And so when you go down a column, so this is really just when you're comparing down a column, and these are your inorganic acids. When I say inorganic, that means they don't have carbon. These are inorganic acids. So HF is the least acidic because there's a lot of overlap. Hydrogen and fluorine are similar in size, so that overlap is kind of strong. Here, bromine is just huge. It's just barely hanging on to this little hydrogen 1s orbital, okay? And this is huge. So guess what? When bromine becomes its conjugate acid, it can absorb that extra electron pair into its little cloud, its big polarizable cloud. And so it's more acidic, a -9. So you're looking at 9, 10, 11, 12 zeros more acidic. So you can see this going down that group, that the halogens, because you're comparing the fluoride, these are your conjugate bases, the chloride, the bromide, and the iodide. And so the bigger the element, the more stable it's going to be to stabilize the conjugate base. So this is going to be your more acidic. And the Pogel exercise works through. Okay, the other one's inductive effect. When you're dealing with inductive effect, it's really just going to be carbon. You're just going to, the examples are always going to be carbon, and you're going to do the hybridization. Oh, no, I'm sorry. I'm thinking the hybridization. Ignore that. Okay. Inductive effect. You're still going to be dealing with carbons, but you're going to be dealing with electronegativity, and the inductive effect is through the sigma bonds. This kind of confuses people sometimes. It's just there's not more than 3 bonds away. So we'll look at some examples, but 3 is the magic number on inductive effects, and they pull, the electronegativity pulls through the single bonds. Single bonds are sigma bonds. So we're not talking resonance. We're not talking about element. We're talking inductive. So here, like you have ethanol. So you draw your conjugate acid here. And here you have this one, and it has these fluorines. And fluorines are electronegative. So what's going to happen here is these lone pairs are going to be the electronegativity here. Remember the dipole? It's going to pull the electrons from that single bond, like a tug of war, towards the fluorine. And we have 3 fluorine. And so when it pulls this through the single bonds, the sigma bonds, that's 1, 2. That's 2 bonds away. So this is going to be very strong. Look at the pK value, 12. Okay. So 12 versus 16 is maybe 4 zeros, 3 or 4 zeros. Okay, so this carbon only has hydrogens and carbons. These are not electronegative elements. And so it's just showing you that. That's an inductive effect. So here, if you rank these, let's draw them out. Carboxylic acid, and this is what's hard when you're first learning chemistry, because you need to take the time to learn to draw these structures. Like I can see that right away that that's a carboxylic acid. I can see that carbon. So it might take you longer. That's okay. That's part of the learning process. Give yourself time. Okay. Now, we're dealing with the same functional groups. They're all carboxylic acids. So if you were to draw the conjugate acids, you would see that these are the conjugate acids. We're not dealing with resonance structures because they're same carboxylic acids, but we're dealing with what's the difference here. This one has one bromine, this one has two chlorines, this one has a fluorine. So this is going to be your most acidic with two. And then I'm going to give you this. This is your third. This is your second. So even though this is electronegativity, because it's pulling through this 1, 2, 3 sigma bonds, this is called inductive. So this would be inductive effect. Okay, the other factor was resonance, and I've told you about that a little bit, but we can also see it here. So you draw your conjugate acid of the alcohol, the conjugate acid of your carboxylic acid, and then can you draw any resonance structures? No, because this is an sp3 carbon. So you have to have unhybridized p orbitals for resonance structures. Here the lone pairs can go and you can draw a resonance structure there. And so we have two resonance structures versus none, or you could just say one if you want to call that one. So what's the difference between those? We're talking 11 zeros, right? 9, 10, 11. So this is the stronger acid, and you would say the factor is resonance structure. And that's what they're showing you here, what I just did. Two resonance structures, only one Lewis structure. Okay, hybridization effect, this is what I was telling you. You're just going to basically, hybridization, you're going to mostly deal with carbon. So this explains why the alkyne, an sp carbon hydrogen, is more acidic. And when you have an sp, you have 50% S character and 50% P character. The S character is more stabilizing. In a conjugate base, this is more stabilizing because the structure with the S is spherical, right? And it's closer to the nucleus. And what's in the nucleus? Positive charge, which stabilizes a negative conjugate acid. So when you have these negatives here on an sp carbon, 50% P, it's going to be more stabilizing. When you take away a hydrogen from an sp2, you have 33% S character, and from an sp3, you have 25%. So the more S character, the more stabilizing. This is hybridization effect. And what's it worth? You know the pKa value here is 25. pKa value here is 50. And I always just do the fives. Okay, so this is a big deal there, folks. That's 20 zeros. Okay, 20 zeros. This is 5 zeros. Okay. And this is just showing you that these, where these electrons are, how their percent S character. Okay, so these are your 4 factors. You do have a POGL on that to work through some models to reinforce this concept. Here we have let's see what we have here. So this, like I said, you want to draw these Lewis structures out. This one, carbon, CH2. I think this was I think this is a typo there. I don't think that's supposed to be there. And then this is, and they're showing you this. So in this case, when you're dealing with this being number 1 and this being number 3, what's the concept? The concept is hybridization. SP, SP2, SP3. This is looks like the top is cut off, so let me see. Slide 39. How to determine the relative acidity of a proton. Well, the other thing you need to be able to do. So, hopefully, the I can statements. From so far, you should be able to draw, predict, and label acid, base, conjugate base, and equilibrium values in an acid-base reaction, because you're going to be tested on that. The other thing I want you to be able to do, I can explain why one compound is more acidic than another. And that's those 4 factors, right? 4 factors that affect the acidity, the stability of the conjugate base. And this one, the third thing you're going to have to be able to do is you're going to have to be able to determine, I can determine the acidic proton in a compound. So this helps if you can find pKa values. So how do you identify the acidic proton? Well, let me just tell you, if it's bonded to a heteroatom, you need to look there, all right? So look there. There's my eyeballs. So hydrogen bonded to an oxygen is going to be more acidic than hydrogen bonded to a nitrogen or a carbon. This is that element effect. Because when you have the conjugate base, the OH, the O negative, stabilizes that, the electronegative oxygen is going to stabilize that negative base, negative charge. That is going to be your number 1. Okay. You can always draw the conjugate base. If you have resonance, resonance always wins. So let's look at something like this. We have tosic acid. This is an important acid for organic. This is an organic acid. What does that mean? That means it's soluble in organic solvents. That's important because in the lab, lots of times you don't want water, no water. So HCl, sulfuric acid, these are inorganic acids. They're always going to be in water. But acetic acid can be, that's an organic, and tosic acid. Now look at the difference here. This is a pKa of 5. Tosic acid is a pKa of -7. That's pretty remarkable. Why? What's the difference? Well, para-toluene sulfonic acid, it has more resonance structures. So that negative charge can go onto that sulfur. Okay, so identify the most acidic proton structure below. Do I have the structure there? I don't have your structure. It didn't convert over. Okay, so I will draw your structure. And you can get this in your notes. So this is where you will get a structure, and you have to find the most acidic proton in that structure. Okay, so this HC bonded to the oxygen, that's kind of like an alcohol, right? A functional group. And that pKa is about 16. This HB is on a carboxylic acid, And so it's going to be pK around 5, right? And it's because why 5 versus 16? Why? What's the difference? Well, one has resonance structures, so that's resonance is a factor. And then we have HA here. Well, HA is on a carbon. And what's the hybridization? It's 1, 2, 3, that's sp3, right? Because we don't have the other hydrogen shown. So an sp3 carbon has a pKa of about 50. So this is going to be your weakest proton. So your most acidic proton in this molecule is going to be Hb. You need to familiarize yourself with common bases and common acids used in chemistry. These are your bases, okay? You might even want to make a sheet of these bases because they're really going to help you. You need to, you see that whenever you see sodium and potassiums, you make them a plus, and then that gives the negative to the oxygen here. These are your alkoxides. If you ever hear me call it alkoxides, these are your oxygen, sodium hydroxide. These are your typical bases, and that negative charge will always go and attack a proton. Here, notice that these get positive charges here, and so the other element will get the negative charge. And that'll be important in drawing your Lewis structures. Characteristics of strong bases, they usually have high pKa values. I would say even higher than 12. Butyl lithium, you see when you make lithium a positive, that's going to give this carbon a negative, and that is a very strong base. So carbon anions. A lot of your bases and your organic bases have a nitrogen, they're amines. So when you start learning your Lewis structures, you'll see that they don't have a charge, but that's a lone pair. Pyridine is a good base, and triethylamine is a good organic base. They kind of smell like fish, rotting fish. And that's a lot of times why you would take a lemon. See my little lemon here? Make my little lemon. Okay, so you put a lemon on your fish. Have you ever done that with lemon on your fish? Well, you're doing an acid-base reaction. So if you have citric acid and you have like an amine, you're neutralizing that so it doesn't smell. All right, so when you have this molecule here, this is aspirin. Aspirin, there's your carboxylic acid. This is why it's called a salicylic acid. This is, and then you have a base there, it can deprotonate that. And you can think about, could water deprotonate that? So if you have water, and this is your base, what's your pKa here? Your pKa here would be carboxylic acid of 5. So that's a carboxylic acid. And then this is your conjugate base. What if that was water? So if that picked up a proton, what's the pKa value? 1.7. So it's going to, in water, it's going to be more towards the protonated form. Okay. I'm just going to go ahead and tell you that you can access these slides. They're on your Blackboard. So in this situation where the slides seem to have not copied over well, you can refer to those. This is just your definition of an acid base. Oh, these are Lewis acids and bases. Lewis acids and bases we're not going to really talk about until you get into organic 2. But Lewis acids and bases, you're not dealing with a proton, folks, okay? Protons are when you assign pKa values, okay? So pKa values are with protons. When you're dealing with Lewis acids, they're usually like empty shells, like BH3. Well, if you look at the structure of BH3, okay, so boron is 3 things, so that's an sp2. And then there's this unhybridized p orbital. So sp2 is flat, right? It's planar. And then it has this p orbital, this unhybridized p orbital, and it's above and below. It's above and below the plane. And what you know about unhybridized p orbitals, electrons go there. So if you have something like ammonia, where you have this lone pair, ammonia, those electrons want to go into an unhybridized p orbital. And so when you put ammonia and BH3 together, so if you take BH3 plus ammonia, what you're going to get, and you're not going to get an equilibrium, you're going to get a molecule that forms a bond, okay? And this will be a negative, and this will be a plus. So that is what you get from a Lewis acid and base. And so they're showing you different Lewis acids and bases. The bases still have lone pairs, but your acids, these are your Lewis acids, they have those unhybridized p orbitals. So what happens is you have this unhybridized p orbital, and like an OH will go and put its electrons there, and then you have a new bond, and so something like that. And then this would be plus, and this is negative, but they overall sum to 0, and they form a covalent bond. But don't trouble yourself around these. We're going to be talking about Bronsted-Lowry acids. They donate and accept a proton, and you can sign pK values. And this is just showing you the covalent bond there. What is important, though, is the concept of electrophiles and nucleophiles. And you do need to learn this because we're going to be talking about it. An electrophile, it's a Lewis acid, but you're going to see me write, you can write electrophile like that. I write electrophile like this. And then you'll see me write nucleophile like this. And the reason why you'll see me do that is a nucleophile has, you got to recognize these. The nucleophile has a lone pair. It could have a negative charge. And you're going to see double bonds and triple bonds are sources of electrons. Nucleophiles are sources of electrons. And they're always going to take those electrons and they're going to go towards an electrophile. So this is how we always draw our curved arrows. And this is going to be important for reaction mechanisms. And so you always draw a nucleophile to the electrophile. And when you turn in POGIL and you do that wrong, I will correct you. And what is an electrophile? Electrophile can have a positive charge, or it can have these unhybridized p orbitals because electrons love these unhybridized p orbitals. That's where it's kind of like the garage for the car. And you always get a new covalent bond. And so this is showing you, this would be an electrophile. You see the positive charge there. And that would also be an sp2. So that carbon has an unhybridized p orbital above and below. And then this is your nucleophile. You can recognize the negative charge. And then those electrons are going from the nucleophile to the electrophile. And then that is going to be a new bond. And this is going to be, this is reaction mechanisms. And so you always, when you're drawing a reaction mechanism, I'll say, okay, where's your nucleophile, where's your electrophile? And you always find that negative charge or those lone pairs, and that's where you start. Here, this is an sp2 aluminum. And so there's this unhybridized p orbital, and these electrons from the chlorine, the lone pair, will go towards the aluminum. And you have to be specific with where you point those electrons, okay? They can't just go in anywhere. They're going to that carbon. And there you go. And then you have to be aware of formal charges there. Okay, drawing products, we will do that more. The curved arrow, and then there's your formal charges. So here, this, remember I said a nucleophile Here, let's make it blue. Be consistent here. I said a nucleophile. This is how I draw them. So see, there's a lone pair there. I mean, a pi bond. And a Lewis acid here. So what happens here is these electrons are going to go and take that, and those electrons will go there. And when we get into reaction mechanisms, you're going to learn to do something like this, and then the chloride is there. And so this is your nucleophile, this is your electrophile. And that's what it's showing you here. And these are reaction mechanisms, and we will practice this more when we get into reaction mechanisms. Identify the nucleophile in the reaction of ethanol and HCl. So in this case, this is your acid, because it wants to donate a proton. It's a strong acid, you know, the pKa there. This is the Bronsted-Lowry. That acid has a pKa like -10. And then we have, you know, this one isn't it, because this is a pKa of what? 16. So this one's going to be your acid. That would make this your base. And now you know to draw these lone pairs there. And then you draw your products. What are your products? And then the chloride. And identify the nucleophile. Well, the base is the nucleophile here. So that would be your nucleophile. This would be your electrophile. And that is the end of Chapter 2. Please work your POGIL models and suggested problems.